Swayam Prabha. Digital India. Educated India.
Students, today we are going to discuss about the solidification of these isomorphous two-phase alloy system, and we are also going to discuss about some variation of these isomorphous ternary phase diagram. So, before that, let me just take you some recap of these ternary phase diagrams. One of the important thing about ternary phase diagram is basically isothermal sections of the 3-dimensional space model. 3-dimensional space model is obviously the best thing to use with, and the space model consisting of a equilateral triangle on the horizontal plane, and the vertical plane it has temperature axis. And I have discussed with you regarding how to measure compositions and how to draw this this space model. So, for the simple system like a ternary isomorphous, in which all the three components are forming isomorphous system with each other is shown here. Okay, this is you see ABC as a ternary isomorphous system, you can see clearly on this picture. Now, as I told you, one of the important aspect of this phase diagram is to take the 2-dimensional projections, and best way of doing is use the isothermal sections, that is section at a particular temperature. So, here suppose if I draw a section at T1, and the way I draw is that I take a triangle same to as ABC and cut this ternary space model with this triangle at a temperature equal to T1. So, what I get is basically this kind of sections, you can clearly see this is the one, that is the another one, okay, that is what is shown. And then this 2-dimensional projection will divide the triangle into 3 regions: liquid, solid and liquid plus solid in between. And the surface bounding curves between the liquid and the liquid plus solid zone is known as liquidus projection, and this one is known as solidus, and therefore I can draw tie lines between them. That is what I discussed with you. Then I can actually take this section at different temperature. You see it is done at T2, I get completely different section than that, and again section is similar, like consisting of 3 zones: liquid, solid, alpha and liquid plus alpha, 3 zones demarcated. And if I take a section at T3 which is much lower than this solidus curve, then I get completely only alpha, there is no 2-phase or liquid phase region. That is something I discussed with you in the last lecture nicely. Now, I have also discussed with the vertical sections, correct. Vertical sections are the sections which are taken at different ways. I can draw this triangle and show you what are the different ways we can take a vertical section. This is A, B, C. So, one of the way of taking vertical section is drawing a line like EF, okay. Draw a line parallel to AB and take a section, correct. This will look like this is okay. I think this is what we are using YZ, let us do that, YZ here, or you can actually take one of the lines as like this, A to C or B rather, okay, this is small p, correct. So, in these sections they look like again similar to like binary isomorphous phase diagrams. The whole diagram section is divided into 3 zones: liquid, liquid plus alpha and alpha, but they are not, because we cannot draw tie lines here. very simple. We can also have a section like this is suppose AMN, the same line but like YZ, but at an angle not parallel to AB, and I have shown you what are the ways it will look like. Another important aspect which I did not discuss with you is that the free energy surface for the ternary isomorphous system will look like this. Binary it is looking like this, for any for the isomorphous system it will look like this, right. This is your delta G, this is A, this is B, XB, correct, and this is what is delta G L. Delta G S will also be looking like exactly similar, okay. There will not much difference. So therefore, whatever you see as a curve, U-shaped curve, inverted parabola is a surface, parabolic surface, correct. That is what is we call Gibbs spin energy surface. Now let me just get into the basic theme of this lecture. We are going to discuss about the solidification behavior of ternary isomorphous system with both equilibrium and non-equilibrium conditions. Well, this is what is a ternary isomorphous system, ABC phase diagram, space model, 3D space model, correct. Now I am going to discuss the solidification of the alloy composition X. So in a binary, as I told you, if I want to discuss solidification of alloy binary between AB, what I do? I draw the vertical line X, correct, composition X, then I start from the liquid, I discuss solidification of the alloy as I move inside the liquid plus solid and finally into liquid. How I do? I draw tie lines, right, that is how I do. I do not want to get back into again to it because I have done to discuss several times. Now in a ternary what happens? As you cool down the liquid from the high temperature, first thing it will do is it will touch, just like this point is on the liquidous surface, this will also touch here on the liquidous surface. This is touching here on the liquidous curve, this is the liquidous and this is solidus, correct. So it touches on the liquidous curve here, on the ternary it will touch liquidous surface here. And what does it touch at temperature T1, at temperature T1 here you see T1 corresponding to point L1 on the liquidous surface. Now as it solidifies here, okay, I think let me draw it here better way because you need to follow it up, and correlation between binary and the ternary is very important. So X, oops, this should not be, it should be parallel, okay. So let me draw it properly, otherwise you will also make mistakes. This is, so I draw a line X, as it touches here I draw a tie line, right. So therefore solid which will form as a composition S, liquid as a composition L, or rather I like again same way alpha 1 L1, correct. So that is what is shown here. This is the point on the liquidous surface L1, this is a point on the solid surface alpha 1, correct, because this is like a conch shell like this. So therefore inside that I can draw tie lines. Now as I, so therefore the first solid which will form as a composition given by alpha. So as I cool it down the liquid, what will happen? The next temperature suppose T2, this is T1, then T2, the solid will have composition given by alpha 2, the liquid will have composition given by L2, correct. Similarly I can draw at T3 alpha 3 L3 and finished done at T4 alpha 4 L4, correct. So this is how the whole thing will be done. Now as you know the solidification is over at L4, similarly solidification will get over at L4 because at L4 solid will have a composition same as the overall alloy compositions. Now this is easy here to follow because this is the space model in 3 dimensional is a very easy things to follow, but in real life everything will not be easy to follow. the space model may be very complicated, and if this is the case, how you are going to follow it up. So, best way of following it up is to basically draw these projections onto this Gibbs triangle, correct, and this is what is done here and shown as a zoom view, you see here. So, as you see, the liquid composition is falling on the liquidous surface given by L1, L2, L3, L4, okay, along these, correct. Let me just draw it like a red curve. On the other hand, solid composition is followed by the points on the solid surface, and they are given by L1 to L4, correct, and sorry, alpha 1 to alpha 4, and alpha 4 and L1 falls on each other. That is obvious, because L1 is the first solid liquid composition to start with before it started solidifying, and alpha 4 is the solid composition which is finally solidified. So, they will have same compositions. So, now I can actually join these crisscross lines to draw the tie lines, correct. The point is, the reason we draw it here is that we can actually then calculate, suppose if I want to know the volume fraction of alpha and at a temperature L1, at temperature T1 basically is minuscule means why it is minuscule, because X is sitting exactly on L1, only at L2 temperature T2 X lies on this point. So, therefore, volume fraction of the alpha 2 will be L2, volume fraction of alpha 2 L2x divided by alpha 2, right, L2x divided by L2 alpha 2 into 100, that is the volume fraction of alpha 2, sorry, a solid alpha at temperature T2, correct. This is the length of this arm divided by the other one. Similarly, you can do the same thing. So, same thing can be done here also, exactly same thing can be done here also. That is the reason actually we show it onto the ternary plot. So, now let me go over to the board and explain you how the tie lines actually rotate, correct. So, that is very important. So, let me just go to that board. So, see, I have drawn these things. So, let me just tell you this is alpha 1, L1, L2, alpha 2, L3, alpha 3, L4, alpha 4, okay. So, now let me just see that this is what is this at temperature T1, correct. This is temperature T2, T3 and T4. Just to show you that if I take the projections at the isothermal sections at T1, T2, T3, T4, that is how it will look like. So, at T1 you have, this is the liquidous projection, this is the solidus projection, and so therefore, there are 3 zones L plus alpha and alpha, okay. I have not written L plus alpha, let me write it, correct. So, the tie line is following like this, L1 to alpha 1. Just now whatever picture I have shown you in 3-dimensional model, if I project it there, this will look like this, and X is sitting exactly on L1. Why? Because this is starting alloy compositions. So, therefore, volume fraction of alpha is very small, or 0 actually almost. Now, if I go to temperature T2, some amount of alpha has solidified, and the composition of alpha 2 is given, alpha is given by alpha 2, and liquid is given by L2, okay, L2, this is L2. Again 3 zones, liquid plus alpha and alpha, X is sitting there. So, now if I want to measure the volume fraction of alpha, this is nothing but L2x divided by L2 alpha 2, okay. Volume fraction of alpha is L2x divided by L2 alpha 2 into 100, correct, that is what it is, and X is sitting inside this liquid plus solid zone, not on point L2 anymore. Then if I come to temperature T3, X is well inside this projection, and if you see the projection carefully, it is starting from A each end, okay, because A here is, B here is the highest melting temperature, C is the lowest melting temperature, and A is the intermediate melting temperature, okay. So, this is the highest melting temperature element, next to this, next is this, and next to is this. So, what actually happens? You see here again X is inside this alpha plus liquid, quite inside, and there are 3 zones, liquid, alpha plus liquid and alpha. So again I can calculate volume fraction of alpha, that is why actually I wanted to draw it. So it is basically L3 x divided by L3 alpha 3 into 100, correct. And if you look at this ratio, this length is all little bit changing, I know, but not much, but L2x is very small. On the other hand, L3x is large, so therefore volume fraction of alpha has increased. Now if I go to the T4 where the solidification has ended, so alpha 4 and x is sitting on each other and L4 is here. So volume fraction of alpha is, volume percentage of alpha is, okay, L4x divided by L4 alpha 4, that is nothing but same as L4 alpha 4 divided by L4 alpha 4 into 100, that is nothing but 100% alpha. Okay. So that is how actually one can calculate the volume fraction of alpha as its solidification gets over. It is exactly same as a binary, binary also you can do the same thing, okay, exactly same thing. So very easy to follow, that is why I always wanted to draw this picture, binary isomorphous phase diagram, liquid alpha, alpha plus liquid. So if I follow it up, I can draw this, this is my alpha composition, suppose this is alpha 2 L2, so I can calculate the same way, here also I can do the same thing. Only thing I have to do is that to draw the composition I need to draw parallel lines that I have discussed with you when I showed you how to calculate volume fraction of phases in a two phase system, correct. So another important thing is that if you look at the tie lines, what tie lines are shifting towards from B to A, okay, they are going from here to there, they have rotated this way, from here to there rotated further this way, they have rotated further this way. So they are rotating anticlockwise. Why they are rotating anticlockwise? Very simple. The melting temperature is changing B to A to C, that is also anticlockwise. So that rotation of the tie lines will be exactly the same as will be following the melting temperature rotation of the elements that I discussed with you in the last to last class. So this is, you must be able to clearly envision that the tie lines rotates in the same way. So whenever you draw these pictures on your textbook, on your notebook or on the board, you must know how to follow it up, which way the tie lines rotate. And this is the major difference from the binary to the ternary. In the binaries, your tie lines are actually very simple, okay, very simple. They are always parallel to the horizontal axis. There is no rotation of tie lines. So that is the major important thing you must you must be able to follow very carefully. Rotation of tie lines. Although as I told you, the tie line positions exactly will depend on how do you measure experimentally. This has to be done experimentally, but theoretically, for understanding this subject, you will be able to follow it up if you know the melting temperature variations. Here A, B, C is B to A to C is what is the rotation of the melting temperature, and that is anticlockwise. That is why the tie lines are getting anticlockwise rotated. This is what is shown in the next curve. Exactly, you see here tie lines rotate anticlockwise in this picture, and again to show you that this is the first tie line, the second tie line, third one, fourth one, and in the fourth case the x point sits on the alpha 4, correct. So this is all together I want to show you. This is the Ternary space model, and these are the 4 isothermal sections where the solidification is shown, correct. So now we can follow up this one very easily, okay. So let me just go back to my earlier picture. I will keep it here and let me open that one and to show you my nicely, yeah. So this is what is the picture available on the in the book of Alan Sprints, and this is nicely done, okay. Here actually 2 sections are cut off, liquid and solid surfaces are cut off to show you the inside ones. In fact, from the book it is connected, you can see here it is connected, correct, okay. So here you can see if I follow this X, L, S, L1, S1, L2, S2, L3, S3 all are shown, correct, and exactly same thing is shown on the Gibbs triangle. So thus with this I think you have got a fair amount of, I would say not fair, I would say good idea about how to follow the solidification path of these alloys. Now question is this is what will happen when when you solidify under equilibrium conditions, but suppose if you solidify under non-equilibrium conditions, what are the, how the things will vary? Well, non-equilibrium condition means the diffusion in the solid is slow. Liquid, it is possible to have a good diffusion and mixing because of convection, but solid it will not be. So therefore, as a binary, as you know, in a binary we call it a coring effect, because solid is in diffusion in solid is slow. Therefore, the every temperature if you form a solid, it will remain at the composition. It will not basically get homogenized with the next solid. Okay. Or let me just explain you taking this picture, very nice. This very nice picture here. So what I mean to say is that this is suppose a T1, this is T2, and this is T3. Okay. So whatever solid I form at T1 will a composition is given by this point. Okay. So I write down alpha 1. So as I cool it down from T1 to T2, I form another solid layer with the composition alpha 2, correct. So the problem in the non-equilibrium case is that you do not provide enough time for these two solid to homogenize, because these two solid has different composition, right. Can you see? Alpha 1 is richer in B than alpha 2. So therefore, in order to homogenize them, B has to diffuse from alpha 1 to alpha 2, and this diffusion in solid is not allowed because of the non-equilibrium nature of the processing. So obviously the last solid which will form will have a composition given by alpha 3, will be forming another layer alpha 3. So that's the way you are developing a composition gradient from the center to the periphery, and that is what is called coring. Same thing will happen here also, even more complex. Here only you have only one element is getting a compositional variation from the center to the periphery, but there in the ternary you have two elements can be also. So this is basically done this way. So at the T1 there will be no much thing happening because you are only going to form the solid. At T2, let me just draw it to show the effect of non-equilibrium things. It will be shown little bit ahead. Okay. This is, so this is I call alpha 2, this is I call alpha 2 prime. Okay. Can you see that this is alpha 2 prime? Okay. So same thing will be happening here also, correct. Let me draw it carefully. So, and this is alpha 3 prime, this is alpha 3. Alpha 3 is sitting on the solidus curve, alpha 3 prime is little bit higher of the solidus curve. And here again, obviously this is alpha 4 and this is alpha 4 prime, this is alpha 4, correct. So as you clearly see, the solidification will not get over at alpha 4 or T4, it will go down actually temperature than the T4, okay. And probably actually it will be, I need to draw another section and this will be little bit down. Sorry. Oops, it's a little bit angular. So this will be some L5 alpha 5, correct. So that is what is happens here also. The way we represent this solidification sequence is by dotted a line like this, correct, and the end of solidification temperature will be T4. Similarly here end of solidification temperature will be T5 because we are showing already 4 temperatures above. So final one will be there. So that is how actually things will happen. So one of the way of showing this solidification non-equilibrium manner is just extend this tie line little bit ahead. Obviously, why? Because it will be more rich in the component which is the highest melting temperature. As you see here, B is the highest melting temperature compound, B is the highest temperature component. So it will be rich in that, Slowly it is shifting. Obviously, initially it was rich in that, then it is shifted to mean between A and B. Finally, it is shifted to A, B, C also, and finally it will solidify at compositions which is different from the original, which will be same as the original compositions. Okay. But at a lower temperature like this. So that is how actually we show the variation of the solidification sequence in the non-equilibrium manner. Okay. So, and this is very important because this is the easiest phase diagram I am discussing with you. I like for you to understand and try to think about it how this diagrams can be used to understand the ternary solidification of different ternary alloys. Well, in the next lecture, although I thought of discussing about ternary the 3-phase equilibrium, because I am only discussing in these diagrams of 2-phase equilibrium. 2-phase means liquid to alpha or liquid plus alpha, correct. There is no third phases existing here. So, I am going to discuss about that, but before doing the next class, I will also show you some variation of these isomorphous phase diagram partially for 5 minutes, and the next 20 minutes I will discuss about this 3-phase equilibrium. Okay.